and I'm a first-year PhD student at the University of Ghent. And today I will be presenting our paper, Maximal Fairness. The goal of our paper was to investigate which fairness notions can be combined in a binary setting while it still remains mathematically possible to satisfy the constraints from these fairness notions. The first work in this line of research were the impossibility theorems. These were created by Tijl and Kleinberg et al., and they investigated a specific case based on the compass case. So they used analogous fairness notions to the one displayed here, namely equal opportunity, predictive equality, and predictive parity. But you might know them as equal false negative rate, equal false positive rate, and equal positive prediction value. However, the work of Tijl also is in the binary setting, while the work of Kleinberg et al. Was more in the risk scoring setting. So they investigated what combinations of these definitions were possible and which weren't. So we have the combination of equal opportunity, predictive parity, predictive equality, and predictive parity as pairwise combinations, and then we have the combination of the three of them. And we can actually see that the combination of equal opportunity and predictive parity is feasible together with the predictive quality and predictive parity one. This was found out in their paper. I did not include the combination of equal opportunity and predictive equality here because that simply maps onto the fairness notion of equalized odds, and we already know that this is a feasible combination as equalized odds is an often used fairness notion. However, when we look at the combination of the three of them, we actually saw that it is not possible. So it's not possible to combine predictive equality with equal opportunity and predictive parity. It is only feasible in certain edge cases, and these cases are if the positive rates are equal in the data sets themselves, or in very certain trivial cases where the system itself is not usable anymore. So we decided to expand this research and to include more fairness notions, and we did that by the use of the confusion matrix. So other works often use a statistic or probability to determine the feasibility, but we decided to go with confusion matrix. We did make one small adjustment to the confusion matrix, and that is that we don't use the absolute numbers anymore, and instead we use the percentages. This does not change anything to the definitions themselves. It just makes it easier to compare the two of them, to compare the two groups together. So as you can see right here, so we have 4 variables in our confusion matrix, but then if we look at the data set themselves, 2 constraints already come up. And that is namely that the combination of the number of true positives and false negatives equals 1 minus the base rate, with the base rate being the ratio of negative occurrences in the data set, and the false positive plus a true negative combination is equal to that base rate as well. These are just properties of our data that construct our confusion matrix from the beginning, so this is important to keep in mind. So we have 4 variables, but we already have 2 constraints. So we can be fairly certain that we can still apply 2 other constraints on this table and still come up with a result. This is the theory starting going forward, and that it will be more difficult to find a combination of 3 or more fairness notions that can still be applied to this table. The first fairness notion that we apply is demographic parity, which maps onto the positive rate in terms of statistics. Then we have equal opportunity as discussed previously, so this is equal to the false negative rates being equal for both groups. Similarly to equal opportunity, there is predictive equality, which just requires the false positive rates to be equal for both groups. A little bit different again is the predictive parity, which asks the positive prediction value to be equal for both groups. And then again, very closely related to predictive parity is the false omission rate parity, and the name already gives it away a little bit. It requires a false omission rate to be equal across both groups. Then we have the overall accuracy fairness notion, which is a fairly simple fairness notion, which just requires the accuracy of the system to be equal across both groups. And then we have a rather special one, which is treatment equality. And unlike the previous ones, treatment equality cannot be expressed as a probability or as a statistic, but rather it is just defined on the confusion matrix. And that is why it is interesting for us to use the confusion matrices in this work, because that opens up the possibility of including treatment equality in our calculations. Now, for the results. So we have our 7 base fairness notions, and then we can start combining them pairwise. What we actually see is that all pairwise combinations of these 7 fairness notions are possible. This is on the one hand expectable, but still it's a nice result to see, because that actually confirms that none of the fairness notions contradict each other. So that means that what is fair in one situation doesn't mean that it's completely unfair from a different perspective. So this is a comforting result to know that none of the two pairwise fairness notions contradict each other. Then we can move on to the combination of three fairness notions, and then we can actually see that only 5 of them remain. So this is also again what we expected, but on the other hand, it is still nice that we have some combinations of three fairness notions that can be combined, because that shows that they have some similarities between them. Otherwise, it wouldn't be possible, because there would be too many constraints on the confusion matrix to still allow a good enough degree of freedom, and not have a constraint system or a certain constraint on our data set. So this was actually the main result of our work. We actually hope that with this work you are inclined to also work, instead of using or optimizing one fairness notion, you're compelled to start working on combinational fairness notions, and maybe not a set combination like conditional use accuracy or equalized odds, but rather have a more free system like we want, because then you can see there are a huge number of combinations that become possible. The second part that we hope will become more prevalent is investigating the combination of these fairness notions. What do they mean? What settings are they nicer? Because we think if you can choose at a more free selection of fairness definitions, that can also result in a more specific constraint set for your certain system, that it can encapture the concept of fairness for that system better. And that was the goal of our research, to give the first nudge in that direction of research. I would like to thank you for your attention.